Okay, let us discuss the next problem. So this problem says chloroethane ClCH2. So this is problem number 15.12. So ClCH double bond CH2. If I treat this compound with HCl, what will be the product? That is the one issue. Now it says, problem says chloroethane adds hydrogen chloride more slowly than ethane. Now if I take ethane, this is molecule is ethane, and if I add HCl, everybody knows what product you will have. You will have a product something like this, CH2H, CH2Cl. So now the problem says, in this case, rate of reaction is very slow. In this case, rate of reaction is fast. So this is chloroethane adds HCl very slowly. So this reaction is slow. So this reaction is slow. So the first problem is slow problem. Now second problem is the product is, let us say I give you the product. So let us say CH double bond CH2 and I have Cl here. If I add HCl here, same thing I am writing here, so this is the same thing. The product is something like this, CHCl, and we will have one more Cl. Okay, so should I write here? And there is no CH2, so there is single bond, and you have CH3. So the second problem is problem of orientation. You see, in this case what we have done, in this case both chlorine is going onto the same carbon. Initial chlorine was here, and following the rest chlorine, next chlorine is also coming out to this position. So the first point is point of reactivity. So this question says this molecule reacts slowly compared to this molecule. Are you getting? So let us call this molecule 1, this molecule 2. So I can say molecule 1 reacts slowly than molecule 2. So molecule rate of molecule 1 is slow than rate of molecule 2. You have to explain this behavior. Can you explain? So rate of molecule 1 is slow than rate of molecule 2. And then the second problem is problem of orientation. Orientation. Now you have to tell me why chlorine is adding at this position, why not at this position. If you add at this position, what will be the product? CH2Cl, CH2Cl. Are you getting? If you add this chlorine here, that is, you can add H plus here and chlorine here, or you can add H plus here, chlorine here. So you have two possibilities. If you add chlorine here, you will have CH2Cl, CH2Cl. But you are adding the two chlorine at the same point. So this means second problem of orientation. Why chlorine is, let us say, call this carbon number 1, or let us say call alpha, this is beta. So this is carbon alpha, this is beta. So the second point is why chlorine is going to the alpha carbon. That is why the orientation is something like this. So why at alpha carbon. So why chlorine goes to the alpha carbon. You have to tell me clearly. Now I will give you a hint. You decide the reactivity on the basis of inductive effect. You decide orientation on the basis of resonance effect. So you have to decide reactivity. So this is enough hint on the basis of inductive effect, and then you have to decide the orientation on the basis of resonance effect. So this is a observed fact, that is if you react molecule, this molecule, chlorine goes to the alpha carbon. This is experimental fact. The second experimental fact is this molecule reacts slowly than this molecule. So we have two experimental facts. First fact, something related to reactivity, that is this molecule reacts slowly than this molecule. This is the one fact. The second fact we have, on this carbon, on this molecule, chlorine attaches on the alpha carbon. So you have to tell me these two results on the basis of inductive and resonance effect. So let me bet for 1 minute. How many of you are able to do this one? Okay, let us discuss. So we have CH double bond CH2Cl. If I add H plus, the first step H plus Cl minus, so this goes here. Now if I add H plus here, so I will have CH, Cl, CH2 and H plus. I am adding H plus, so carbocation I am forming here. Why I am forming this? We will explain. This carbocation is resonance stabilized by this chlorine. So I can write another resonating structure of the same molecule. Something like this, HC double bond Cl. So this is lone pair, here you have one more lone pair and plus charge, and then you have CH2 group. So this is a resonating structure I can write for the same molecule. So why I am making carbocation here? This is because this carbocation is resonance stabilized by the lone pair of chlorine. So this says something about orientation. So now in the next step, if Cl minus attacks, so now I have only one option. This Cl minus has to go on this carbocation. So this Cl here, and then CH2. So now my problem of orientation is over. So we have solved the problem of orientation. So we have why this chlorine attaches to here, because carbocation formed is this, and this carbocation is resonance stabilized, and that's why chlorine that is coming will attack on this carbon. So problem of orientation is over. We have done the problem of orientation using the resonance effect. We have said earlier you have to use the resonance effect to show the orientation. So problem of orientation is over because this is the plus R effect. Now let us discuss why this molecule is less reactive than the ethane. So this molecule, this is because now you see the carbocation that is formed in this case is this. If you have a ethene CH2 double bond CH2, in this case if you add H plus, you will get a carbocation that is CH2 plus, and this side CH3. So CH3, now there is no, in this case you see what is the problem? You have a Cl group, so that can even take electron by minus I effect. So this Cl group has a tendency, are you able to see or not? So this Cl group is basically have a tendency to take electron, so minus I effect, so that destabilizes the carbocation. But in this case there is no Cl group, so that no one is there that can destabilize the carbocation. So you can say in this case carbocation gets destabilized by the minus I effect. So minus I destabilizes the carbocation. Destabilizes the carbocation, and that's why in this case you can say rate of this is low compared to this. So see, you see, if I try to summarize all this thing, I can say this carbocation has two effects, plus R and minus I. If somebody wants to say this carbocation is minus I effect destabilizes but resonance stabilizes, so why this carbocation is not totally stabilized? Because resonance effect is greater than the inductive effect. So if the resonance effect is greater than inductive effect, so I can clearly say this carbocation gets stabilized. Why I am calling this carbocation gets minus I effects, that is more? Why I say that this carbocation gets destabilized? Now once again, this is the experimental fact. To support the experimental fact that this is less reactive and this is less reactive, this one, are you getting? This molecule is less reactive and this ethene is more reactive, we take the help of minus I effect, and to basically say something about orientation, we take the help of plus R effect. So basically what is resonance effect and inductive effect is basically my theory. So R and I is just a theory, it's nothing else, it's a theory. So to explain the experimental condition, we use the theory, something like this. If you see electron, sometimes it shows a behavior of wave and sometimes it shows behavior of particle. So when we have behavior of particle, in that cases we do experiment. If I have experiment that shows the behavior of particle, then we take the particle theory of electron. If we do some different experiment, in that case my experiment result can be validated only if assume electron is a Bare, for that case, we assume that my theory is a bare theory. Same thing. I have experimental condition, I have to give theories. And resonance and inductive effects are just theories. So in one situation, my resonance